Welcome everyone. This is our first webinar, yeah, for the 2022 fall. And so welcome everyone. Thanks for joining us this afternoon here in Austin. It's actually a nice sunny day. Like it's probably going to be kind of hot, just like it's been here in Austin for the last who knows how many days now. So thanks for taking your time out this afternoon and joining us. We really appreciate it. Really appreciate your time and attention. My name is Charlie Day. I am the Director of Training and Professional Development here at the Texas Advanced Computing Center and the Design Safe Training Lead as well. So if you haven't been to Design Safe in a while, there's a new headline story about bridges under pressure from researchers at UC Davis, who actually are another one of the 2022 Design Safe Dataset Awards. Speaking of the Dataset Awards, today we have a special for you. We have another one of our 2022 Dataset Awards giving a talk, and we'll get to that in just a little bit. If anybody has any feedback for us, we really appreciate it. So here's a QR code that takes you to our surveys. Just take your phone, grab a photo of it, follow the link, and if you can answer a survey, that'd be great. It helps us plan these webinars better, when to have them, what topics you all might be interested in. If you have a topic that you'd like to present a Design Safe webinar on, please get in contact with us and we'd love to hear you, and we'll see if we can schedule something out. So, and moving forward, so today we have one of our 2022 Dataset Award winners. They are going to be presenting on a prototype scale physical model of wave attenuation through a mangrove forest of moderate cross-shore thickness. They're going to talk about their data curation and then the opportunities for data reuse as well. So today we have Tori, who's an associate professor at the University of the U.S. Naval Academy. And she's interested in better understanding wave-induced forces on coastal structures. And with her, we have Kieran Kelty, who is another civil engineer who works as an eco-engineer at CBEC ECO Engineering and develops hydraulic models for both riverine and deltaic systems. And I guess he enjoys implementing NNBF designs and proposed design alternatives for these projects. It's good to be your hobby being what it is that you do. So thanks so much for joining us, guys. They'll be talking about a natural and nature-based infrastructure system that's rapidly gaining interest as hazard mitigation, coastal infrastructure protection alternatives to conventional shoreline hardening techniques. So they're going to talk about the motivation and overview of their prototype scale experiment and what findings they came across, their data archival process, opportunities that exist for reusing their data, and their planned and where they're planning and going with their tests in 2023. So with that, without any further ado, Tori and Kieran, thanks so much for joining us. Thank you for taking your time out of your day. We really appreciate it. And I'll be handing the screen off to you. By the way, everybody, if you have any questions, there is a Q&A section to this webinar. Type your questions in there, and as the presentation goes, some of those might be answered during the presentations. Some of them will just wait till after the presentation's over and answer them then. So thank you very much. And with that, let me stop my share and hand it off to you all.
Thanks, Charlie. Go ahead, Tori.
All right, thanks, Charlie. Can you guys see my screen?
Yeah, looks great. Thank you.
Yep,
awesome. Thank you. And thank you so much for that great introduction. And we're really happy to be here to present some of our experiments that we did in the large wave flume at Oregon State University Nahiri Experimental Facility. I'm delighted to present today with Kieran Kelty, who was our man in the flume. He really took the lead on these experiments as part of his master's work and now is an engineer at CBEC Eco Engineering. Also presenting today on behalf of Dr. Dan Cox and Dr. Pedro Lomanaco, who were the other PIs on this experiment. So a very brief outline of what we'll be talking about today. A lot of motivation and background. I think there's a growing interest in natural infrastructure, nature-based features, and with that becomes a need for fundamental understanding of how these systems perform on an engineering scale. So sort of what got us involved and how we were able to quantify some of these performance metrics for these systems using our large-scale prototype scale physical model. We'll talk a little bit about lessons learned from the data curation process, which was really beneficial to work with TAC and the design safe experts, and then also some opportunities for reuse. So I think this has been really one of the grand challenges that we're facing today as a society is how can we adapt effectively to a changing climate with non-stationary conditions, and how are we going to adapt our coastlines, which have high population densities already and are really becoming increasingly exposed to severe storm events. And so you can see three examples of natural and nature-based system concept designs. The first in the upper left-hand corner is the big U around New York City, which was proposed after Hurricane Sandy, basically including stormwater parks for storm surge mitigation, flood storage to protect lower Manhattan. If you move clockwise, you can see this is a proposal for Boston Harbor. It's called the Emerald Tutu. Each of these little green dots you can see surrounding Boston are little pods of vegetation, which again are supposed to help to attenuate waves and mitigate storm surge. And then the final picture in the bottom left-hand corner, you can see this is actually an implemented design at the Fort Pierce Marina in Florida, which incorporates both conventional coastal engineering systems. You see those T-head breakwaters protecting the marina, but it serves as this island breakwater system, which also includes submerged aquatic vegetation. They have mangrove and dune grass plantings, trying to serve as additional habitats to create these environmental benefits, as well as the engineering services that are needed for the marina. So the motivation for this study really came after Hurricane Irma about 5 years ago in 2017. Here you can see three panels. Each of these panels shows an overhead of the lower Florida Keys with the storm track making its way right through Cujo Key, sort of this C upside down C-shaped key kind of in the middle. After the storm, we performed damage assessments in Key West, which is boxed on the left-hand side of the storm, and then Big Pine Key, which you can see on the right-hand side of the storm. Variable wind intensities, water inundation depths, and significant wave heights. And after the storm, we performed structural damage assessments. And really the original goal of this study was to understand the relationship between hazard intensity, wind speed, storm surge elevation, also characteristics of the structures themselves, such as the lowest horizontal member elevation, and relate those conditions to the structural damage. We surveyed 263 waterfront residential structures. So all of the structures we surveyed were right on the shoreline. And one thing that became quite apparent to us in the field was that a lot of the structures we surveyed were very, very similar in terms of the footprint that we observed. So you can see this overhead panel in the upper right-hand corner. All of those building footprints look nearly identical. That's not by accident. That's actually part of the Naval Air Station support housing. And so, you know, many of these houses were built at the same time, same sort of cookie cutter blueprints. But what's different is you can see that there's varying shoreline management on a parcel by parcel or house by house basis. So up on the top, we have sort of a house that had a sandy beach, sort of a stretch of mangroves as you move further down. And then finally revetments and some spotty mangroves moving further down in the image. We observed these four major shoreline archetypes that you can see on the slide: mangroves, sandy beaches, which typically completely got washed away by the storm, revetments and bulkheads and seawalls. Those are our more conventional coastal shoreline stabilization approaches. They had variable performance. And so we documented these in addition to documenting damage to each structure which had that shoreline. And the major outcome from this study was this relationship we found between the hazard intensity measure, which we've plotted on the x-axis, and the damage state of the structure, which we evaluated on a 5-point scale, with 0 indicating no visible damage and 4 indicating that the structure was completely destroyed or was removed from its foundation. Our hazard intensity measure we defined as the elevation of the wave height with respect to the lowest horizontal member of the structure. So as this value increases, you expect higher damage states. As you can see, if you just look at the data points, it looks a little bit like a cloud. So that was not really great news when we first looked at this. However, when we broke this out by shoreline archetype, we found that the vast majority of the structures where we saw different performance than expected were these structures that experienced high hazard intensity measures, but low damage states. And most of them had mangrove shorelines with few exceptions. And so what we found was that mangroves provided significant protection to Hurricane Irma's waves and storm surge compared to other shoreline treatments. This isn't necessarily new information. There have been a lot of studies that have shown that mangroves can provide protection during tsunami events over very, very large spatial scales. The new thing about our study was we found significant performance in terms of wave damage attenuation over fairly small cross-shore widths. As I mentioned, there have been some other studies that have shown really great results in terms of wave attenuation through the rhizophora mangrove. Particularly rhizophora are mangroves that have these above ground prop root systems. So there's a lot of work that they do to attenuate wave heights. I've listed some of the physical models there. All of them, though, were done at reduced scale. So we had a model that we did at the directional wave basin a couple years ago at Oregon State, where we looked at wave force mitigation by these parcel scale mangroves, saw significant reduction. Similarly, Maza et al. And Sheng et al. Were able to quantify drag coefficients and wave height attenuation through larger cross-shore forest thicknesses, but again, all done at reduced scale. These projects typically try to calculate this wave height decay coefficient. I won't go into detail over all of these terms, but essentially this wave height decay coefficient is a function of the vegetation parameters. So things like the projected area, density of the forest, an empirical drag coefficient, which is what sort of the goal of a lot of these physical model experiments is, and relating that to hydrodynamic parameters. So looking at, the incident wave height, incident water depth, and incident storm surge. The challenge when you have a reduced scale physical model is if you're calibrating your drag coefficient, how can you actually apply that in real life? And so that was one question we wanted to answer using the facilities at Oregon State University. And so if you're not familiar with the facility at the OH Hinsdale Wave Research Laboratory, I highly recommend you make a trip to Corvallis. It's a phenomenal place to do testing of all sorts, but specifically we've used it for physical model experiments looking at wave height transformation through the built environment. We've done that in the directional wave basin, so that's this image here on the right-hand side. And the experiments that we'll focus on today looking at wave height attenuation through idealized mangrove forests. And so for that, I'll toss it over to Kiernan, who really was our lead on the experiments, to talk about the physical model experiment.
Thanks, Tori. Hi, everyone. I'm Kiernan. And so I'm going to step us through the prototype physical model experiments that we did at the large wave flume for Oregon State. So first, I want to cover some project goals that we have for the experimentation, where we first wanted to quantify our mangrove performance at full scale, like Tori just mentioned, particularly for wave attenuation and wave force reduction. We also wanted to evaluate the effects of mangrove forest density on those parameters of wave attenuation and wave force reduction, primarily talking about how many trees in an area. So if we had more trees in an area versus less trees in an area, how that would affect those two wave attenuation and wave force reduction parameters that we just talked about. And we also wanted to come up with a lighter methodology to quantify key geometric characteristics of our forest that Tori mentioned, like projected area and density, so that we could then put that into the wave attenuation equation and get an accurate result. So we attempted to do that in this study as well. And finally, we wanted to compare to the previous results that Tori mentioned, particularly the Maza et al. Studies and the Chang et al. Studies that were previously done. So for our physical model layout, we use a large wave flume, which can be thought of as a slice of shoreline, as you see in the top right-hand side, where the flume itself is about a football field long and 15 feet deep, if you can kind of picture that in your head. Where for our mangrove forest, we had a flat section in front of it, then followed by the forest that was about 60 feet in length, followed by then another kind of a flat section, and then we had a test wall, which we used for portion of our testing to get an idea of what was the wave force reduction after the waves had passed through the mangrove forest and then hit our wall. So we measured that using pressure gauges. Next slide, Tori. Oh, I got ahead of myself, excuse me. We'll get there. But for the actual instrumentation that we had in the flume for the forest itself, we deployed an array of wave gauges as well as pressure gauges, which here are highlighted by the red box. And so those pressure gauges, which are seen here as orange rectangles, excuse me, are the primary instruments that we use to quantify the wave attenuation for this experiment. We recently did some analysis doing the wave force reduction. However, we won't present that in this talk, but I'm sure it'll be available later, and Tori would be happy to talk to you about it later on. You can go ahead, next slide. So here's the pressure gauges on the array for our test wall, which you can think of as a coastal structure or a representative structure in this case, where we had pressure gauges all the way from the bottom of the wall to the top to be able to resolve that wave force and the pressure profile on that wall. And you can also see here we have Pedro Lamonaco, the Wave Lab director for scale on that test wall. So you can see that each portion of the wall itself is about 6 feet in height. So it was pretty large. For our mangrove forest layout, we tested 2 different mangrove densities: a high density, which had 50 mangroves within the large wave flume, and then a low density, which had 25 trees within the large wave flume. We also tested a baseline case where we had no mangroves within the large wave flume, just so we could measure the attenuation and the effects of the flume itself on the exact cases that we were testing. So then we could later subtract it from the high density and low density tests that we did, and ideally get just the effect that the mangroves themselves are imparting on the waves. We also placed the test wall in for half of the layouts that we tested, for a total of 6 layouts that we deployed within the flume for a total of 1 month of testing. For our actual tree specimen, we used previous field studies, which we'll touch on in the next couple of slides, as well as a modified equation by O'Hara et al. 2013, where we had a trunk diameter of around 11 centimeters with 14 roots per tree. And the highest root coming up to about my shoulder, which you can't see me in person right now, but is about 5.5 feet, 5 feet or so up. And we use PVC and PEX material to represent our trees and construct them. And we use those materials based on previous material analysis studies that we found. So here's some of those previous field studies that we looked at. These range from areas in Southeast Asia to the Caribbean here near the United States. And we're primarily looking for the type of species. So Tori mentioned the Rhizophoria species was the main one we were testing. So we wanted to look for studies that had those species highlighted in them, as well as the trunk diameter, or DBH as it's noted here in the table, as well as the mangrove forest density, so we get an idea of what the range of values would be to test. Here's a continuation of that table, just showing the breadth of studies that we considered. And now we're moving on to specimen construction. So here's some photos of us actually pulling that PEX material out and to be able to create those roots. And then we're staging the trunks themselves, and finally preparing the large wave flume test section to deploy those trees. Where in total we used just under 4,000 feet of PEX material for our roots and around 625 feet of PVC material for our trunks. Here's some more photos of the construction. So here we're filling in our test section on the left-hand side. Then we're using the help of a lot of very nice grad students, as well as undergrad staff at the large wave flume, to help us thread those roots through the different trees, and finally pouring concrete into the large wave flume to cap our test section and help secure those trees themselves. In total, the actual start to finish construction, once we started placing trees, was 1 week. After we got the mangrove forest in place and we were letting the concrete cure, we then took the LiDAR scans of our forest, and we took scans before, in, and after both the high density and low density forest for a total of 8 scans per forest. We then took those scans, stitched them together, and created a 3D representation of our model forest, so you can see on the bottom left. And once we took that forest, all those scans and created the 3D representation, we were able to go in and choose a representative repeatable slice, or stencil in this case, where we took slices of each different stencils, looked at the projected area for each stencil, compared them to each other, and took an average with variability. So if you go to the next slide, Tori, we can see here, you can see what a slice would look like if you're looking at a first-person view. You see the picture on the left, then what the LiDAR sees, and then finally averaging all those stencils together on the right-hand side, where we have the horizontal error bars showing that variability in the projected area. And we did that for both the high-density and low-density forests, where we took different slices, averaged them, and compared those two average profiles to each other and found minimal difference. And essentially what we're capturing by doing this one representative profile is we're able to use this one profile to represent the entire variability of the forest itself, but also just use one profile to then place into the wave attenuation equation that Tori highlighted earlier on. So for wave conditions, we tested both regular and random waves. For regular waves, for those who aren't familiar, kind of symmetrical and repeatable waves where every wave height period is the same, whereas random waves can vary more, and oftentimes what's seen more out when you're looking at the coast. And we tested a range of wave heights and periods, as well as water depths ranging from just under 2.5 feet to 6 feet in depth. And here's some photos from the experimental trials, where we have a shallow water depth on the left-hand side, where you can see the roots are exposed and the waves themselves are mainly interacting with the trunks and roots at the lower water depth. And then at the higher water depth on the right-hand side, they're mainly interacting with the trunks and some of the top of the roots as well. Here's some more experimental photos, where we have a deeper water case that I just talked about earlier on the left-hand side, as well as a shallow water case where we have wave breaking in the mangrove roots themselves. And finally, we have a large splash event on our test wall, just to show and highlight the range of conditions that we tested for the experiments. That one splash event on the right-hand side was maybe 10 to 15 feet up in the air from the actual top of the test wall. So after we did all those testing and we measured all of our cases, we then took the measurements of the wave height and plotted them against each other. Here I'm showing one trial that we ran for all of the 3 different layout scenarios of high density, low density, and baseline without a test wall, where we have wave height on the Y, and then we have location of the different instruments that I showed earlier on the X. And if we focus in on just the diamonds, those diamonds are the pressure gauges that I mentioned earlier, where if we look at the diamonds on the left-hand side, they generally start at the same wave height. So meaning that at the start of the mangroves, high density, low density baseline, the wave height was generally the same. But then after the wave progresses through the high density, low density forest, the wave height begins to decrease more, where we can see that the darker diamonds here represent the high density case, whereas the lighter green represent the low density case, and finally the lightest represent the baseline case. And essentially showing that the most wave attenuation happened with the high density mangrove forest, followed by the low density, and then finally the baseline case. But there was some attenuation from the baseline case itself. So it shows the need to do baseline case runs as well. So we took that change in wave height, and we did a wave attenuation calculation, where we have wave attenuation here on the left on the y-axis, and then we have water depth on the x. And we can see 2 groups here. The first group is the darker circles compared to the lighter colored circles here, where the darker represent the high density layout compared to the low density layout. And we can see for all water depths, the high density mangrove forest has more wave attenuation than the low density mangrove forest. The second grouping would be by water depth here. And we can see that on the shallower water depths, we have higher amounts of wave attenuation for both low density and high density mangrove forests. And that essentially showing, and that coincides with the higher amount of projected area, whereas at the deep water cases, we have less attenuation where we have less amount of projected area for those waves interacting with the mangroves themselves. We then took those wave attenuation values and we calculated a drag coefficient, or CD. And this is a non-dimensional parameter that can be used for engineering design, as well as comparing to the previous reduced scale tests like Maz et al. And the Chang et al. Studies. And we have it here, a drag coefficient on the Y with the Reynolds number on the X, and which is another non-dimensional parameter that helps describe the turbulence of that particular test. So we calculate the drag coefficient for both the regular and random waves, as you can see here. We then compared those to some previous studies, particularly the Chang et al. And Maz et al. 2019 study, which is here. We have those results for the regular and random drag coefficients plotted against those studies, which is both of those studies are kind of bunched up here on the left-hand side, and they don't really coincide or agree with our study results. However, when we did a rescaling approach based on fruit, we shifted all of the results to the right, and very nicely, they all agreed with our study results, where we have the Maz et al. Studies kind of operating in our higher Reynolds number cases, even going beyond our Reynolds number cases, and then the Chang et al. Studies kind of operating here on the left-hand side. We then were able to fit an equation through those. As you can see here, where we're fitting an equation through the entire 3 studies results, and we're presenting this equation to use mangroves for engineering design. And these can basically, this equation can be used in numerical models as well as in actual real life design cases. So now for a touch on data curation with DesignSafe. It was really helpful with the DesignSafe videos on YouTube. I can't remember exactly who made them, but whoever made them was fantastic. They're really great and helpful to be able to figure out how to use DesignSafe well for our data curation process. It was also a collaborative workspace because I was able to kind of build out a framework and then let Tori know, hey, you can go look at our framework. And she was able to just log in really quick, look at it, make edits herself, and then let me know when it's time for me to look at it as well. And it was also allowed us to link previous projects as well as future projects going down the line of any work that's related to this moving forward. Tori, I'm sure you also have some comments of the process as well.
I do, Kiernan, and thank you so much. I think really just to highlight what Kiernan said about how helpful the DesignSafe resources are, and particularly the office hours were very beneficial for us working with Maria to organize the data, upload large data sets. One other plug I'll make for uploading data on DesignSafe, particularly since we were doing these experiments sort of right in the thick of the COVID-19 pandemic in winter of 2020. We really I found this to be extremely useful since I wasn't able to travel to Oregon in person, to be able to see data uploaded on sort of a semi-real-time basis, look at interesting data sets, and really a great place just to keep a repository for collaborative work. The final thing I'll mention about the DesignSafe and the data curation process is one nice thing that it also let us do is get a DOI for our project before we submitted our description of the experiments for publications. And so we were able to cite our data within the publication and hopefully point people who might be interested in using this data set as a part of future work, which I'll talk a little bit about some of the future work and opportunities, I think, for data reuse of this specific data set, as well as some of the work that we have ongoing and planned for the wave flume this summer. So moving on to studies, I want to highlight that have continuing use of this data set. As Kiernan mentioned, half of our trials included a test well where we measured the wave forces on the mangroves, we measured the wave forces on a wall that was positioned directly behind the mangroves. And so that study was really led by William Mitchell as part of his master's work. He's now moved on. He's an officer in the US Navy. And so he's done a lot of great work though, looking at how forces can be reduced by the mangrove forest and how existing methods for predicting forces do when you think about wave attenuation. And one really promising result that he found was that when you account for the wave height attenuation, our existing methods for predicting forces analytically are still fairly robust. And so the mangroves do enact this wave attenuation, but as long as you can get that right, you'll still get a good estimate of the total force. Another study is being done by a current master student, Kayla Ostro, and she has done some great work that she presented recently looking at how important these wave decay factors are and what's the importance of considering the scaling effects when we're looking at these calibrated drag coefficients. And so here you can see one plot where based on numerical model runs, we're looking at the observed wave height decay versus the predicted wave height decay for considering scaled drag coefficients, so based on the equations that Kieran showed just a couple slides ago, or if you're using drag coefficients that are not calibrated to account for these reduced length scales that may be used in smaller scale studies. And the good news is when you account for these scaling effects in laboratory experiments, you get pretty good results between predicted and observed wave height attenuation. The bad news is that you have to make sure you're accounting for those scale effects. So we saw that when we don't account for scaling effects, it can significantly impact these predictions for wave height decay by up to a factor of 4. Additional future work, it's really exciting to do things in the lab because you can have a really controlled space to measure specific impacts of changing water depth, changing wave height or period on things like wave height decay or wave force reduction. The next step, though, is to relate these to the additional uncertainties that you add when you go into the field. And so we have a couple of efforts right now looking at measuring wave height attenuation and wave transformation through field mangrove test sites. One of those studies we did was a couple years ago in Key West, Florida. This was a really fun experiment where we got to kayak for work, but essentially what we were doing was measuring boat wake transformation through mangroves, looking at the transformation, the boat wake signal sort of at the fringe of a mangrove, the middle of a mangrove stand, and then at the rear, the leeward side of the mangrove stand, next to a highly trafficked recreational boating channel. The mangrove stand itself was quite narrow, only about 12 and a half, 12.6 meters cross store thickness. And looking at the results, it was very clear to see sort of this reduction in wave height from these boat wake signals, which were quite easy to distinguish from the overall tidal and wave signal of Key West. It was very calm on the days that we were recording. So each of these boat wake signals was a very clear pulse of 7 to 8 wave heights. And we looked at sort of these representative wave heights from the fringe to the middle to the rear, and we saw a clear reduction between all those cases. We also looked at the spectral energy transformation and found that within the sort of shorter period waves, so that's sort of the 1 to 3 second waves that you might experience when you're looking at boat wakes, we saw greater attenuation than we did for longer period waves. And so that was also good news because I think for some of these more chronic stressors, such as boat wake events, you can see high impact of nature-based infrastructure, such as mangroves, on protecting shorelines from erosion. In addition, we're hoping to also look more at some data that we collected last year of long-term measurements that were on an island west of Key West under wind wave forcing by storms. And so we collected some overland flow data while Hurricane Ida was passing by over, I think, around August, late August of 2021. And that was some exciting experiments and really just excited to look at the data in a little bit more detail. The final ongoing work study that I will give a plug for is the need to be able to synthesize nature-based infrastructure with existing conventional infrastructure, whether that's to expand the lifespan of some of the aging infrastructure we have around our coastal highways and other systems that are just reaching the end of their design life, or whether that's integrating nature-based infrastructure in a space where maybe you're confined and you don't have enough space to enact, a 200-meter mangrove forest, but you can put in some nature-based solutions in addition to some conventional structural engineering methods. And so We have a NSF-funded project that kicked off in January, where we're looking to understand these fundamental interactions between green infrastructure, so things like mangroves or marshes, and gray infrastructure, so these conventional revetments, seawalls, and how that can change the overtopping performance of a engineered hybrid system. Those experiments are planned for this summer, 2023, at Oregon State University in the Nahiri Experimental Facility. So please contact me if you are interested in learning more about that or would like to come out. We're really hoping to get some folks out there who are interested in this work. And then just to conclude, I think this was a really fun project to be a part of. Lots of things that we learned. I think there's a lot of avenues for future work. Looking at the performance of not just mangroves, but also other nature-based systems like reefs or marshes or islands. And I think looking at some of these methodologies to characterize field protocols for how do we get these projected areas of mangroves and how do we relate that to drag coefficients and how can we ultimately incorporate that into a design standard is really going to be a next big step for the engineering practice. And so I think our results show that mangroves can be effective, but there's a lot of work that's still left to be done. So I'd like to take a second just to acknowledge our funding sources who were supportive of this work. The long list of names you see are people who were helpful to this project in many, many ways. I'm sure we're missing some names on there, but really great to be part of this effort. And with that, we're happy to take any questions that may have popped up in the chat, and feel free to reach out to us too at our email addresses if you want to follow up to discuss in more detail.
All right, wonderful. Thanks, Tori and Kiernan, for a great presentation. So if you have questions, feel free to open up the Q&A panel and I'll moderate those. And maybe to get things started, I'll ask a couple, if that's okay. My first question is about the mangrove trees themselves. Are these pretty robust with respect to sea level rise? I did notice that their attenuation kind of decreased as the water height increased. So I'm just curious about how sea level rise might impact their efficiency, and will the trees grow taller or thicker in response and things like that?
That's a great question, Scott. And so there have been some studies that have looked at the ability of mangroves to keep up with sea level rise. Basically, one thing that mangroves do because of their above ground prop root system is they can trap sediment. So where there's an adequate sediment source, many studies have shown that they're right now keeping pace with rising sea levels. Now, what happens with accelerating sea level rise and whether sea levels start to rise more quickly in some areas is definitely a subject of debate. And I will say too that when you incorporate sea level rise plus storm surge, it's important to consider what zone you're in, whether you're in that trunk zone where you might expect less attenuation, or whether your roots are high enough that they can provide that additional benefit.
Another thing I'll add on to that, Tori, if I could, is that we tested a flat, basically our mangroves were completely on a flat section, whereas natural shorelines are sloped. And so maybe while the start of that forest, Scott, might be like the trunk section where we were showing where it has less attenuation, maybe the majority of the rest of the forest would be in the root section where there might be more attenuation. So you also have to think about where that sea level rise and that storm surge is acting on the forest and how much of it too.
All right, great. We do have a question now from Demetrios. Great work. Have you thought about modeling approaches for simulating the interaction between mangroves and incoming waves?
That's a great question. And that is a little bit of the ongoing work that we're doing. So not to put anybody on the spot, but our master's student, Kayla Ostro, is right now using X-Beach to model this interaction of wave vegetation and specifically looking at what happens to the waves themselves. X-Beach is a little bit different than some other models where here you parameterize the mangrove as a system of cylinders. One thing I think that we're interested to do is to compare results that you might get from that type of model with something you might get from an open foam model where you're really modeling every single route and taking a lot of computational expense, but getting a really, really good result.
All right, thanks. I had another question too, just about data publishing. So Tori, you mentioned that it was great to be able to get a DOI and publish your data and then cite it in your paper that came after. You know, one thing I've heard people be concerned about is kind of having their data scooped, right? So you publish the data before you've written the paper, and then somebody else can come along and sort of use the data before you publish. So I was just wondering if you had that concern or if that happened to you or anything like that.
Well, now I do. I'm just kidding. That's a great question, and I think that's a very valid point. One thing I think that was nice for us with the timing is we were writing the paper at the same time that we were publishing the data, so we sort of were able to put the DOI in finally at our final revision stage. That timing worked out really well for us. I would say that you would need a lot of, from the physical modeling side, you need so much understanding of what went into the design of the experiments that hopefully it would be hard for somebody to scoop out data and kind of beat you to the main results. And I think especially in this Nahiri community, people are pretty willing to collaborate and share, but definitely something to keep in mind.
Yeah, I've always been skeptical of that concern, but people do voice it, and it's commonly cited as a reason to not publish data. But anyway, thanks for your perspectives on that. And then, yeah, I did have just one other question too. I've done centrifuge modeling as part of I did it as part of my PhD, and then a few more as a professor. So these scaling effects are, when you do a smaller scale model, are really important. And one thing we've done is to scale the viscosity of the water. So we mix it with something that makes the viscosity higher. And we're doing probably much smaller scale compared to the prototype, so it may be more important. But I'm just wondering if that's a thing. Like, do people scale viscosity in order to make smaller scale models?
That's a great question. To my knowledge, typically the viscosity is what breaks down. We typically just use water, and so we break the Reynolds number when we scale using Froude similitude. Or we introduce scaling effects to the Reynolds number, some broken. But I think that's an option. I would say probably at the scales that were considered for our comparisons, they're still relatively large. So if we were to reduce things very much, I think there might be more significant scaling effects that showed up just because you have these interactions between the water and the roots that just don't happen, when you're using these larger scales. One benefit, I think, of these experiments is that we showed that if you're accounting for these scaling effects, you can get away with these moderate scales, these 1:6, 1:7 scales, which are quite frankly much easier. You don't have to buy out all of Home Depot's PVC in order to create the model. So it's nice that you can use them as long as you take those effects into account.
Yeah, and you probably can't fill up the wave flume with maple syrup or something, right?
I don't think Pedro would be very happy about that.
I'll ask Pedro about that.
All right, great. We do have another question in the Q&A now. Great presentation. I wanted to ask about the effect of aging or wear and tear of the PVC and PEX when exposed to harsh waves.
We did have some wear and tear, but generally the trees held up great. I wouldn't say that there was any catastrophes on the trees themselves. They held up pretty well, but I could imagine if we had some natural mangroves in there, we would definitely see some trees getting taken away.
Yeah, that's kind of a follow-up question I had. Do these trees get damaged in big storms when the waves come and hit them, roots get torn and stuff like that?
Yeah, that's an excellent point. And that's one thing that we did not consider in these experiments. We sort of assumed we have these indestructible mangrove systems. But really, there's two competing elements here. There's the performance of the system, assuming that the system doesn't fail, and then there's the survivability of the mangroves themselves. And so I think a really important next step for future research is to be able to quantify these upper limits where the mangroves might be uprooted, or maybe there's a really, long-term flooding, or it messes the salinity up, and so just ecologically the system's not going to survive. And it's something you are introducing when you're incorporating nature-based infrastructure that I think is important to be able to quantify.
Or for the red mangrove, a major loss to their canopy. that can be pretty important for them, as it's conducive for them to be able to kind of exchange salt and be able to get water out, but then also release that salt that they took in from the seawater.
All right, great. There are a few more questions. It took a while, but people are really asking good questions now. Have you considered modeling the wave flume with historic hurricane data?
Great question. Kieran, I'm not sure if we have done this specifically for this experiment. I know several of the conditions that we selected in terms of wave conditions were representative of what you might expect during a tropical storm or hurricane. We have also in other tests looked at creating storm hydrographs, so looking at how does the storm progress over time, and you know, what might that look like in terms of loads. But I think it's really important to be able to relate, these real hurricane situations to, you know, what we're modeling in the flume.
All right, thanks. And here's one that's a geotechnical question. So I really like this one. It would be interesting to include looking at the root soil interaction when they're under hydroloading. Is that something that you've considered? I saw you cast concrete to kind of anchor the roots, but have you considered?
Well, you can ask Tori for her summer experiments in 2023.
It's something we're definitely interested in. Sediment is really interesting, and I'll say it as someone who's not a geotechnical engineer, I think it's very hard, but also very exciting to work with. And so we've talked to some folks who are quite interested to look at potential root sediment interactions, and at least as a starting point, you know, maybe be able to start to quantify some of those effects. But I think it's very important, particularly as, you know, again, if we try to ultimately interpret these results for what that means to a field site, being able to understand how the sediment is interacting with the roots, where that sediment is going, is definitely important.
All right, and Scott says you should also include pore pressure measurements, which I will second. That's a good one. All right, so that's all of the questions. I think we can hand it over to Charlie. I know, Tori, you have to teach a class, I think, in a little while, so good timing here. Are you there, Charlie? All right, it looks like Charlie may have stepped away. So I don't have that QR code, but I can mention some of the things that Charlie would say if he were here. Please do the survey so that you'll be emailed a survey link as well. Oh, he is here.
Yeah.
So you can
sorry, my headset battery just stopped, so I couldn't get back to Zoom. My apologies for that.
Those things happen. Natalie told us we should not be talking about how great all the webinars have gone because we're going to jinx it. So that was our hiccup.
All right. So yeah, let me get that QR code back up. And why does Zoom keep disappearing on me today? All right. One more time, Zoom. There we go. Share screen. So yeah, thanks Tori, and thanks Kieran for your presentation. And I could definitely understand why your data set was one of our award winners this year. It was very cool and it's very interesting, especially somebody who does not have a civil engineering background. I'm more of a data analyst guy. So once again, our Design Safe Training Archive is located at designsafeci.org/learning-center/training, or just pick Learning Center off the top. All of our previous Design Safe webinars and links to our YouTube training material is available there. So when this webinar gets curated and set up, you'll find it here in our archive as well. So thank you. Once again, here's the QR code for our survey. Please feel free, please fill that out for us. It gives us some great knowledge on where to take our future webinars. So thank you. And thank you all the attendees for your great questions. And thank you, Gal, for answering that. So once again, thank you, Tori. Thank you, Kieran, for joining us this afternoon. And of course, the rest of the Design Safe team that makes these webinars happen. If you have any questions after the webinar is over, feel free to hit us up on Slack and ask the questions there, or email us at training@designsafe-ci.org, or fill out a ticket on Design Safe help tickets. Once again, thank you so much for joining us this afternoon. We hope you all have a great day, and we will see you all next time. Thanks again, everyone.
Thank you.
Thank you.
Hey, and good luck.